Today we will be doing Gauss's law. In this chapter, we will learn that electric field, when it passes through a surface, it has something called an electric flux associated with it. To understand electric flux, imagine that you have drawn a perpendicular to this surface. This perpendicular, we call it the outward normal. Now this perpendicular, it gives the direction of the area vector. So suppose this surface area is delta S. So the direction of area vector is given by the outward normal to the surface. So the flux due to this field through this area is defined as delta phi equal to E dot delta S. So this is the definition of the flux of this field through this area. Now, when you consider a closed surface, a surface which is completely closed, like a sphere or a closed cylinder, then if you take an element of area on the surface and find out the flux of the electric field in this region through this element of area ds, and if you integrate it for the entire surface, then that gives you the total flux of the electric field in this region through this surface. So the symbol of flux is phi. In this integration I have put a symbol in the middle. This represents closed integral. So the total flux is closed integral E dot ds. So whenever there is a closed surface, you find out the flux of the electric field through an element of area, and then you integrate that for the entire surface to get the total flux. Now we will revisit two topics. Plane angle and solid angle. We will revisit these two topics, plane angle and solid angle. Suppose there is a plane angle theta and the radius is r. So you know that this arc length is r theta. So the arc length corresponding to a plane angle theta is given by s equal to r theta. Or you could say that the plane angle is given by arc length by radius, and in fact this is measured in radians. So the plane angle is measured in radians. Now suppose you have a plane area, and let us say that this area is delta S. In that case, the solid angle symbol is omega. It is given by delta S divided by r square. So the solid angle at a point is equal to the plane area subtended, which subtends that particular angle at that point, divided by r square. So this is the definition of solid angle. Now when we understand solid angle, we need to understand that the line joining the point to the center of the plane area, it may or may not be along the area vector. In this particular diagram, the line joining the point to the center of this area is along the area vector. But it may not be the case. What I mean to say is, suppose you have a diagram like this. So in this diagram, the area vector and the line joining the point to the center of the area, they form an angle alpha. If that happens, then the solid angle is given by delta S cos alpha by r square. So you could say that this is a more general form than this. This is a special case when alpha is equal to 0. Otherwise, the formula for solid angle is delta S cos alpha by r square. Now suppose you have a closed surface. So for a closed surface, the solid angle will be equal to the total area of the closed surface divided by r square. So that will be equal to 4 pi r square by r square. That is equal to 4 pi. So this is a very important result, that the total solid angle at the center of or at any internal point of a closed surface is always 4 pi. Just like in in case of arc length, the total angle at any internal point is always 2 pi. So similarly, the total solid angle at any internal point is always 4 pi, right? Now, suppose you have a plane curve and there is a point outside like O. So this is the plane angle. Now, if you start closing the curve, you will see that the plane angle will start decreasing, and in fact eventually the plane angle will become 0. So at any external point, the angle subtended by a plane figure is always 0, or rather in case of a closed surface, the total solid angle at any external point is always 0, right? At any external point, the solid angle for a closed surface is always 0, and for any internal point, the total solid angle is always 4 pi. Now imagine you have a charge q inside a closed surface, and let us say that you have an area delta S on this surface. The field is E, and this is the normal to the area, and let us say that the angle between the normal to the area and the electric field is alpha. So as you can see, the field due to the charge q will be q by 4 pi epsilon naught r square, and in this diagram we can take this distance as r. So the flux of the field through delta S will be given by q by 4 pi epsilon naught r square dot delta S, or you can say q by 4 pi epsilon naught r square into delta S into cos alpha. So this will be the flux of this electric field through this area. Now if you want to find the total flux, then in that case the total flux will be equal to Q by 4 pi epsilon naught into summation S cos alpha by R square. Now you know that summation S cos alpha by R square is the total solid angle at any internal point, but this is a closed surface, so total solid angle at any interpoint will be 4 pi. So that means the flux will be equal to Q by epsilon naught. Now, if we had done this calculation for any external point, not internal point, in that case what would have happened? In that case, this particular expression if we try to find the total flux, then for any external point, the total solid angle is 0. So that means the flux will also be 0. So that means that the flux of the electric field through this closed surface is equal to Q divided by epsilon naught. So this is known as Gauss's law. So what exactly is the statement of Gauss's law? That if you have a closed surface and if you find the flux of the electric field through that closed surface, then it will be equal to Q by epsilon naught, where Q is the enclosed charge. So this is Gauss's law. So remember one very important thing, that in Gauss's law, the Q on the right hand side is the enclosed charge, whereas the flux which I have written on the left side is due to all the charges present in this region. Because remember, I am talking about the flux through this surface. So through this surface will be for every kind of charge in that region, whereas on the right hand side Q is the enclosed charge. So this is Gauss's law and this is the proof of the law. Okay, now what are the applications of Gauss's law? First of all, suppose there is a conductor and I have introduced a charge Q in this conductor. It's a solid conductor and I want to know what will be the distribution of charges after I have introduced the charge. So now what I will do is that I will consider an imaginary closed surface inside this conductor. For this imaginary closed surface, you know that flux is equal to enclosed charge by epsilon naught. Now you know that this is the interior of a conductor. So the interior of a conductor cannot have any electric field. So the electric field will be 0. So the flux will be 0. That means the enclosed charge will be 0. So if you introduce a charge Q inside the body of this conductor, it will not stay, because for any arbitrary surface like this one, the enclosed charge will always come 0. That means the charge which you have introduced will appear at the surface of the conductor. So this is application of Gauss's law number 1. The charge inside a conductor cannot be present. If any charge is introduced, it will always appear at the surface of the conductor. So this is application of Gauss's law number 1. Then we move on to application of Gauss's law number 2, that is field due to uniformly charged sphere and first of all at an outside point so field due to a uniformly charged sphere, and we want to find out the field at an outside point. Now suppose there is a uniformly charged sphere whose radius is capital R, and there is a point P whose distance from the center is small r. I want to find the field at the point P. So I am drawing an imaginary sphere, this dotted one, which is centered over here, and I will use this imaginary sphere to find the field. First of all, looking at the diagram, it's pretty clear that the field will point radially outwards. So let this be the direction of the field. So by Gauss's law, the flux of this field about the surface will be E into integral ds that is equal to E into 4 pi r square. So this will be the flux through this dotted surface, and let us say that the total charge enclosed in this uniformly charged sphere is capital Q. So we are getting field at the point P is equal to Q by 4 pi epsilon naught into r square. So this is the formula to find the field at a point P outside a uniformly charged sphere. Now there is another possibility that the point may be inside the sphere. So suppose the point P is inside the sphere, like I said, this distance is small r, this distance is capital R. Now I am considering the point P is inside the sphere. So as usual, the field will point radially outwards. Now if I apply flux, then it is closed integral E dot ds, that is equal to E into 4 pi r square. According to Gauss's law, this should be equal to the enclosed charge by epsilon naught. Now for this particular diagram, the enclosed charge we can calculate like this. For this dotted sphere, the volume is 4/3 pi small r cube, and for the big sphere it is 4/3 pi capital R cube. So Q by 4/3 pi capital R cube into 4/3 pi small r cube by epsilon naught. So Q into small r cube by epsilon naught capital R cube. So this is equal to E into 4 pi r square. So now you will see that finally the result is coming. E is equal to Q into small r by 4 pi epsilon naught capital R cube. So this is the formula to find the field at any internal point of a uniformly charged sphere. Now we come to the next application, that is field due to linear charge distribution. Now we come to the next topic, that is field due to linear charge distribution. Suppose this is a linear charge distribution. And I am interested in finding out the field at a point P, which is at a distance r from this linear charge distribution. So I will draw a cylinder centered on this charge distribution with radius small r, such that the surface of this cylinder has the point P on it. Now this cylinder must have a length L. Suppose L is some arbitrary length. If you look at this diagram, then the flux of the field will be given by E into integral ds, that is E into 2 pi RL. This will be the flux of the field through this cylinder. Now let us say that charge per unit length is lambda. So by Gauss's law, this E into 2 pi RL should be enclosed charge by epsilon naught. So if the charge per unit length is lambda, it will be lambda into L by epsilon naught. So this will give us E is equal to lambda by 2 pi epsilon naught R. So this is the next application of Gauss's law, that is field due to linear charge distribution, and the answer is lambda by 2 pi epsilon naught R. Next we come to field due to plane sheet of charge. Suppose you have a plane sheet Suppose you have a plane sheet and it is a uniformly charged plane sheet. There is a point P at a certain distance near this sheet where we want to find the field. And this point P is placed near to the sheet. The sheet has infinite dimensions, length and breadth are infinite, and the charge density is sigma. That means charge per unit area. Charge density is sigma, that means charge per unit area is sigma. Now the thing is that the flux of the field through this closed cylinder, I have drawn a closed cylinder whose one end contains P and the other end is symmetrically located on the other side of the sheet. So the flux through this cylinder is E dot delta S, that is equal to E delta S. Now this is for this end of the cylinder, and similarly there will be another E delta S for the other end, because you can see that here also E and delta S are collinear just like over here. And for the curved surface, everywhere the field and area vector are perpendicular. So that means the total flux through this entire cylinder is 2 into E into delta S. Now the charge density is sigma. So sigma into delta S is the total charge inside this cylinder. That divided by epsilon naught should be equal to the flux. So from here we are getting E is equal to sigma by 2 epsilon naught. So this is the next application of Gauss's law. The field at a point near a infinite plane sheet of charge. Now we come to field near a charged conducting surface. Field near a charged conducting surface. So this is a conducting surface. I am considering a point P. We are interested in finding out the field at the point P. So this will be the direction of the field. This will be the area vector, and I am also considering an area on the curved surface. So this is the area vector and this is the field at that point. Now one end of this cylinder passes through P, the other end is located inside the body of the conductor, and this is a uniformly charged conducting surface. So once again the charge per unit area will be sigma. Now the flux of the electric field through the surface will be E into delta S for this part, because you can see that the area vector will point away and the field is also pointing away. The flux of the electric field due to this part, the opposite end will be 0 because it is in the body of the conductor where the field is 0, and for the curved surface also the flux will be 0 because area vector and field are perpendicular. So this is the total flux, and this is sigma into delta S by epsilon naught. So when we solve, we are getting E is equal to sigma by epsilon naught. So this is the formula to find the field at any point near a charged conducting surface. There is another way to obtain this formula. You know that a charged conducting surface can be thought of as two parallel sheets separated by some distance, and for each of these parallel sheets the field at the point P will be sigma by 2 epsilon naught. So the total field at the point P will be sigma by epsilon naught. So the field at the point P due to each of these sheets will be sigma by 2 epsilon naught. So the total field will be sigma by 2 epsilon naught plus sigma by 2 epsilon naught, that is sigma by epsilon naught. Now we will discuss potential energy of a uniformly charged sphere. Suppose there is a sphere whose radius is r and the total charge inside the sphere is equal to q. Now let us say that we are assembling this sphere and at some point of time the radius is x, and from there onwards the radius has been further increased by dx. Now the thing is, the charge density of the sphere is q by 4/3 pi r cube, that is charge per unit volume. So that means what? In this particular diagram, the enclosed charge will be 4/3 pi x cube into q by 4/3 pi r cube. So that comes q into x cube by r cube. So this is the enclosed charge, and the potential at the surface will be q by 4 pi epsilon naught x. So if you apply this the value of small q, you will get q by 4 pi epsilon naught r cube into x square. Now remember that you are increasing the radius by dx. So to increase the radius by dx, you have to add some more charge, that is 4 pi x square into dx multiplied by the charge density, that is q by 4/3 pi r cube. So after simplification, it comes to 3q by r cube into x square dx. So this will be the total charge that has to be added for increasing the radius by dx. Now the work done to increase the radius by dx will be potential at the surface into dq So that is coming 3q square by 4 pi epsilon naught r to the power 6 into x to the power 4 dx. Now this is the work done for increasing the radius by dx. So the total work done is equal to this, which finally gives 3q square by 20 pi epsilon naught r. So this is the total work done in assembling the entire sphere, and this is actually the potential energy of the sphere, 3q square by 20 pi epsilon naught r. Now let us see potential energy of a spherical shell. Now suppose we are talking about a spherical shell which is basically having a total charge q and radius capital R. Now suppose, let us say that you are bringing charges from infinity, and at some point of time the charge that has been brought to the surface is small q. So the potential at the surface will be q by 4 pi epsilon naught capital R. Now you want to bring some more charge dq. So the work done will be v into dq. That is q dq by 4 pi epsilon naught r. So the total work done will be the integral of dw from 0 to q, which comes q square by 8 epsilon naught r. So these are the formulas: potential energy of a uniformly charged sphere and potential energy of a spherical shell, and that brings us to an end of the chapter Gauss's law.